Alright, hello and welcome back. We're going to finish up these slides today and then start some new ones. So we stopped down here. How can we ever trust our programs? One way is to test them, to make up some test cases to figure out if it's doing the right thing all the time. In the good cases, when the user gives us normal numbers, and also in the bad cases, where users give us weird things, or almost weird things. Okay, so that's where we stopped, and this is a very nice way of trusting a program, to test a program. You can't write every test in the world, so you don't know if this is going to work for 1,000,000 but not 1,000,001 unless you test it. So there are some holes left by testing. There is a stronger method. There is a way to make correct software from the very beginning, and that's what I want to talk about now. Here are a bunch of ways that you might go about doing this. The first way is to write two versions of the same program, like put two different teams doing the same thing, maybe a blue version of the thing and a green version of the thing, and make sure that they agree on their outputs. Like whatever they give back, they better agree, and if they don't, then you need to signal an error maybe. Okay, that's like a self-checking version of a program. It's redundant, it's wonderful, and the programs make sure that their outputs are correct. So maybe if they're supposed to give back a number between, I don't know, 0 and 42, if they ever try to give back 43, the software, it's checking its own output. It makes sure that it like brings it down to 42 or something. Okay, so that's one way to make correct software. You just prove that they're always going to check their outputs and with themselves and with each other. That's one way. Another way, a way that I am a bit of a fan of, is to prove things about your program. You can prove that programs are correct, which is really cool to think about. You can use fancy math to make sure that your program will never even get into this bad case. Yeah? Which is wonderful. Wonderful to think about. So that's the second option. The third option, which is something that I studied in grad school, was how to analyze a program. It's essentially you run the program in math and you see if there are any problems with it. So like if you say x equals, I don't know, 42, and then you say x equals x plus 1, there are analyzers that are smart enough to know that like right here, the only possible value for x is it must be 43. Okay, this is a simple example, of course, but the rabbit hole goes quite deep. Okay, so that is program analysis, which is very fun to think about. It's kind of like in between self-checking and proofs. So program analysis is something that Python's doing before you run it, because it's making sure that you don't have any stray tabs or things like that. So you can make it as fancy as you want to make it. And then there's something that industry really likes, which is specification languages. So you essentially give a mathematical formula for what you want the program to do, and then you make sure that the program that gets written actually follows that formula. So it's like, okay, the output, I don't know, here's like a specification. The output must be less than or equal to 42, something like that. So you can write this. There's a way to write this in math, and one language is called Z because it was made by Europeans, so it's not Z, it's Z, and you can translate this into a specification language like Z, and then run maybe an analyzer to prove that the program matches its specification. So that's another thing that can maybe combine different ways to write correct software into one big chunk. Okay, and then finally, let's just talk about them. All of them require something special, okay? They require you to think before you start writing your program, okay, which is something we don't like to do all the time, but it's very, very helpful, and it is the way to make it correct in the first place, right? You have to specify up front exactly what you want the program to do. Like, okay, it better be less than or equal to 42, the output. You have to say that somewhere, otherwise there's no way of knowing if it's correct or not. You have to say what you want, right? And at the end of the day, these can all go horribly, horribly wrong because you might not know what the program should do. Your specification can still be incorrect, which is really unfortunate, but that is the truth. Maybe the output should have been less than 40, and you didn't know, because you didn't design that piece that needed it to be less than 40. You thought that 42 was good enough. So you have to check the specifications, and so there's like a rabbit hole, like who checks the specification? It's who checks that the specifications are specified correctly. It just goes on and on and on forever. But at least when you do it, you can have some level of confidence. Okay, so this is a bunch of ways to make correct software, and I'd be happy to talk about this with you more in office hours. It's a field that I am a fan of. Okay, so let's go to some real-world examples of all this now. The best one especially for like program analysis and things like that, is airplanes. So you definitely want your airplanes to be safe, right? You don't want any software crashing while the plane is in the air, right? So back in the day, air traffic, it was controlled by humans, right? They were talking over the radio, and maybe they had some radar, and they're telling people what to do, and they still do that to this day, right? You're supposed to usually trust the human. But people made some nice software. The Traffic Collision Avoidance System, or TCAS, I guess, and it is inside of the plane itself. So here's your plane, boop, boop, and it is like a little beacon that is sending out information to other planes who are maybe over here doing things, and they can talk to each other, and they can see how close they are to each other, okay? And it can figure out if those two planes are about to hit each other. And it has software that's going to tell the pilots how to avoid collision. Maybe it's going to say, okay, you need to decrease altitude. You need to increase altitude. And then they'll miss each other, yeah? So that was the point of this software. It's quite helpful because humans make mistakes, right? Maybe the air traffic controller was busy and they didn't see this imminent crash, right? So, unfortunately, it kind of cried wolf because the original version of this software that they put in the planes to like prevent these crashes, it was sending a bunch of false alarms. Maybe there was a huge distance between these airplanes, and so even if they were at the same altitude, there was no problem. But it was telling them, oh no, you're about to crash, do something. And so when you cry wolf, people stop listening to you, right? So everybody was like, okay, I'm not going to trust this ever again. What's the point? And the problem with that was software gets better over time, right? So they actually made it so that it was very, very accurate, highly accurate, and unfortunately, one collision happened when one pilot followed the system, like, okay, it was telling them to decrease altitude, and the other pilot ignored it because they're like, I don't trust this thing, and they followed the air traffic controller. So they told them both to decrease altitude, maybe. Okay, so that collision could have been avoided if everybody listened to the actual software, but that was something that wasn't a thing back in the day. And now, I guess a happy ending that is good for us as programmers is people trust the software now more than the human. So everyone is now required to disobey the air traffic controller and trust the little beacon, trust the little piece of software, the traffic collision avoidance system. So isn't that fun? That is something that is very, very helpful, and it's going to save lives if people follow it. So that's a nice little thing, I think. And that brings us to another question, another philosophical question, like, we're trusting computers to save our lives now at this point, and it's working. Do we maybe trust them too much, though? And this would be a great debate topic for class. Well, I guess you could argue with that example from the previous slide, maybe we don't depend on computers enough. Maybe we should be trusting them more often, right? Because they're better at us at some things. But maybe, again, we should just not be using them at all. So let's ask our Kantian and utilitarian friends, should we always look to computers to solve our problems? Is that going to help us? So Kant is all about free will, right? He would probably say, well, nobody's forcing you to use a computer. We don't have to do anything you don't want to do. So if you want to do addition on paper to do your taxes, go for it, dude. That's the idea. It's all about personal freedom. And then Mill, I would probably think that Mill would say, yeah. I think that he would see that computers are doing quite a lot for us, especially during the pandemic, right? We're all using software to learn, to work. So these things are improving our lives in a bunch of new ways every day. So I think Mill would be all about the yes, and Kant would probably be more about the no. Okay, so those are my thoughts, but of course you could probably argue the opposite way if you tried hard enough. So maybe we should revisit this question a bit deeper, like computers, we're relying on them to save our lives, right? Do they really make us safer? I guess we have this one idea of this traffic collision avoidance system that's helping, but are they really making us safer? And I think like Mill would use all this stuff to prove that the answer is yes. So in your car, there is ABS. I don't know if you guys still have to learn about when you take like driver's ed, what to do if your car does not have ABS in it. You have to like keep on pumping the brakes, right? Because otherwise you'll start skidding and you will end up hitting the car you're trying not to hit. So ABS just makes it so you can slam on the brakes and it'll do the right thing. It won't let the wheels lock. That's wonderful. Okay? And then the check engine light, of course. It makes it so that you don't have your car blow up on you. You can take it in before something goes horribly, horribly wrong. So it knows when something's amiss, and you can go and fix that problem by taking it in. And then airplanes, of course, you got, in addition to the traffic collision avoidance system, you have autopilot. So the pilots can take a break, and everything will still be nice. The airplane is not going to crash in the meantime. It's going to stay at the same altitude with the same heading, right? Okay. Then we have home security systems, which is quite a nice thing, I would think. You have cameras now that can prove that somebody was there if they try to break in, things like that. And I guess my question for you is, what was the security system that we had before electronics? And I think my answer would be, I guess you bought a lot of dogs probably, right? That was your security system back in the day. So I guess you can argue both ways, like just keep the dogs, we don't need a security system. But a lot of people like having peace of mind and cameras, right, these days. Phone passcodes, I know we've talked about that in an essay, right? But that is at least useful when people maybe shouldn't be looking at your phone. They try to touch it, but they don't know your password, so they can't see anything. It's quite nice. And then also, all of our money is hopefully being kept safe by computers, right? They are keeping track of how much money we have and making sure we don't have zero balance. They make it so that we can see how much money we really have, and maybe that will help us spend it more wisely. There's also two-factor authentication with how you log in, right? You log in on your bank, and maybe if you haven't logged in on this this computer that you're about to log in on, it's going to send you a text, right? To make sure that you are really you, and it's not somebody trying to break in. So that's quite nice. Quite nice to have. Okay, so I think I probably made you think of more questions than answered things for you in this slide. So that is kind of the point of this entire set of slides, I guess. You need to be your own boss when it comes to technology, and I want you to be thinking about these questions, like, is it worth it for me to use this technology? That is all I could ever hope for you getting out of this class. Okay, so that is the end of these slides, and now it is time for some new ones. This is a fun topic, artificial intelligence. Okay, are you ready? Let us begin. So, the first thing that I want to talk about is Moore's Law, and it's a popular little law. It's more of like a pattern that somebody named Moore saw. Oops. Why can I not draw? The dude's name was Moore, and he noticed a pattern So it became coined as Moore's Law. So let's talk about that. That is going to give rise to faster and faster computers that eventually become intelligent, for some definition of intelligence. Okay, so I'm going to try and answer this question for you. How fast are computers getting faster? I promise this question really does make sense. They're getting faster, but how quickly? Yeah? So enter Moore's Law. This was invented by Gordon Moore, and I believe he was working at Intel at the time. And the observation was, it's a law. It's not like perfectly proven. It's not always going to be something that is going to continue, but it's happening so far. This pattern has been upheld. So what Gordon Moore saw was that the number of transistors in a chip, so think of like your computer has a little motherboard, and it's got like your RAM sitting in it, boop, boop. And then you also have the CPU. So we're talking about the CPU right now, okay? It's the thing that is like thinking. It is the brain of your computer. So I'll draw a little brain. Okay, so that's what we're talking about right now. The number of transistors you can put inside a chip, namely a CPU, is going to double, and it has been doubling every 2 years or so, okay? So this is exponential growth. This is like, okay, we first had 2 transistors, then we had 4, then we had 8, then we had 16, so on and so forth. This gets really big real quick. This is an exponential growth, okay? That is the idea, and that's quite nice because the more transistors you have, usually, the more you can do, the better your CPU can think, and it can do more operations at once, okay? Usually that was the case. So for a while, it meant that computers got twice as fast, yeah? Now, this is more or less still true, but we kind of got around the problem. So let me try and explain this. So eventually, you want to pack a bunch of transistors into a chip. You need to like put power into each of them, right? All of this is electronic. It runs on energy. We started running into power limits for processors, so we couldn't make them twice as fast forever. We kind of peaked at around 4 gigahertz, if you know these words. And I think the H needs to be a capital, and the Z needs to be lowercase. There we go. So you don't really see chips getting faster than this unless you like cool them with liquid nitrogen, right? So that's about as fast as we're getting these days, and a lot of CPUs, probably yours, are even slower than this. Okay, so we started running into power limits, so we couldn't make them twice as fast, even though we were putting in double the number of transistors. So that's when we started stacking things. We started using multi-core architectures, which is like, okay, we have a CPU, but that CPU has a bunch of little CPUs, which each run at a slower clock speed, so they're each like 2.5 gigahertz, but now we got 4 of them, yeah? So they can work on 4 different things at the same time, okay? That is essentially the idea. Again, this law, invented by Gordon Moore, Moore's Law is not going to last forever, because eventually we're going to get down to the atomic level, and we're already having problems at the atomic level. You can't make things smaller than an atom, right? We're having trouble with electrons fleeing because we're making the transistors so small right now. So we're about to hit this wall, but it has been super fun, okay? For now, the law is still going. It's wonderful. One thing that we also did to like put more things in the same amount of space is to start using 3D technology. So like they started stacking the transistors on top of each other, kind of. That has helped a lot too. I'd be happy to talk to you about this. This is something that is the topic of, if you're interested and you continue, CSCI 45, which is like the last class that you would take here with computer science. So that's what we talk about in CSCI 45. Okay, so here is proof that it really is working. Moore's Law really is a thing. Here is transistor count on a log scale, okay? So log scale, when you go up a linear amount of space, you've increased exponentially, okay? So see how we're going from 1,000 to 10,000, and you'd think that, okay, we'd be at 100,000 up here. No, we're at 50 billion. So log scale, linear means really exponential, okay? and then here is time. So you can see that there is a nice line going on here, and because this is a log scale again, this is exponential growth. So let me try and zoom in so you can see what's going on here. Boop. Back in the day, these transistors, there weren't a lot. There weren't a lot in these transistors. So like the very early Intel CPUs down here, Intel 4004, A8008, Motorola 6800 was a very popular one back in the day. We're talking 5,000 transistors, guys. Look at that. That's nothing. That's really nothing. And they were doing work for us back then. They were nice. So just imagine how many of these you would have to like fit into a warehouse to be as powerful as your phone these days. It's crazy. Even in the 90s, like with the Pentium processors, if you've heard of those were very popular. Those are only about 1 million transistors. That's crazy. What in the world is going on here? And now, if we get into these days, we got your Intel processors, your Core i7s, your Apple processors, like in your phones and your iPads, and now your Macs. All this stuff is still following the trend. We're a little bit above it actually right now, which is nice. It seems. And so we're kind of maxing out up here at billions of transistors. That's where we are right now. Like 25 billion transistors. It's crazy. Okay, so I encourage you to look at this. It's a fun little slide, but that is Moore's Law. Computers are getting fast, quickly. Okay, hopefully that makes sense. Let's see how we're doing on time. Yeah. All right, so now let's get into the real meat. Let's talk about artificial intelligence for real. So I want to tell you about how computers think, okay? Because they're thinking. They are doing some form of computation that at least seems like thinking, maybe, if you don't want to go so far as to say that they do think. Let's talk about how good they are at thinking. Okay. I should probably first define artificial intelligence, and you'll see it, you've probably seen it shortened as AI instead, so maybe I'll say AI instead of artificial intelligence, fewer syllables, right? So, of course, artificial intelligence, I've kind of defined it for you, it's when machines think, right? But what does that really mean? So, the idea is they can perceive their environment, whatever that is. Maybe they're put in a very special environment where they can only see like 5 feet around them in all directions. That's still an environment, and they can use that information to make choices. That's very important. That's a very, very key facet of artificial intelligence. And those choices that they make kind of maximize their utility. They are a utilitarian breed. Computers are utilitarian. They like to make choices to achieve those goals. Whatever you program is whatever they think is most important, right? You tell them what is important and they will go and do it. There are a ton of little subfields of AI, though. So you have your robotics, and that's when you actually make physical things that move around and interact with a physical environment, which is very, very fun. You may have heard of Boston Dynamics, which is a company that likes to make robots that like run really fast and like can jump and move things on their own. It's very cool. Go look these guys up on YouTube because it's very fun to watch them do things. I think they made like a Christmas video or something. It was very fun where they had a bunch of these robots dancing with each other, because why not? So that's one subfield of AI, but there are more. Probably the most common these days is machine learning. So it's not when you have like a piece of special made hardware that's moving around, it's more you have software that is using a very, very small piece of the environment. Maybe it has a camera to do something. Like, so maybe you're doing face recognition, you're doing like digit recognition. For the post office loves to do that, to figure out the zip code to send your mail to, so a human doesn't have to look at it, right? So that's all machine learning. And then a subfield of machine learning is neural networks, which is very fun to think about. They're trying to make brains inside of software, yeah? And then you have your good old stats, because really, secretly, machine learning is just a buzzword for applied statistics, okay? That's all it is. So you can totally use good old statistical methods to do some kind of regression and figure out, okay, this is the trend, let me follow this trend, let me make choices based on this trend that I have, that I'm seeing with all this information that I'm getting from my sensors, okay? That is the idea. Those are some nice little definitions of AI, okay? So let's now look at some examples of artificial intelligence. So a very common one back in the day with like those handheld cameras that weren't in phones, right? They were like cameras that you would buy just to take pictures. You remember those? It's been a while. So they like to do like blink detection. They were a fan of that. And so blink detection is just a machine learning technique. And this is a nice another nice topic that goes to show that they probably tested that on a bunch of white people, right? You've seen probably videos making fun of the fact that it doesn't work for all races of people. That is unfortunate, and that is again about equity in computer science. So blink detection, it's a machine learning technique, and what it does is, I think you can imagine what it's trying to do. So, and I'm going to spell out for you on the next few slides exactly how machine learning works. But let me give you a hint as to how in the world a computer is looking at a photo and determining whether or not somebody's blinking. Okay, so the first thing it needs to do is find the face. Yeah, it needs to essentially, in its mind, it doesn't have to do it on the image, it has to draw a box around a face. And the idea is faces look pretty unique, right? So they can look at an image and be like, okay, I'm looking for ovals. Looking for ovals, and maybe there's some hair, so some more or less oval-shaped things. And so then they're going to draw a box around the ovals. That's essentially their idea. That's how they find the faces, in essence. They can do some fancier things, but let's pretend it's just looking for ovals. And then once they found the face, they start looking for the eyes, right? And so they know, like, okay, if you ever took like a class on drawing, you know, the eyes are about halfway in between the top of the head and the bottom of the head, right? It's smack in the middle with you, if you include the hair, right? Right in the middle. Okay, so they're going to start looking there. They found their oval, let's look in the middle of that oval. And then they're going to start looking for white, okay? Because everybody's eyes, regardless of their color, they have white around the actual eye, right? So that is the idea. They're going to look for that, and maybe they find the whiteness, and they mark the fact that the eyes are open. And if they don't find the whiteness in the middle of the image, then they mark that the eyes are closed. Yeah? So that's essentially what the computer's doing. But you can get fancier. So let me talk to you a bit more about machine learning, what's really going on here. Okay, let's talk about how it works. So I've put this into 3 steps. Okay, step 1, step 2, and step 3. This is how machine learning works. Technically, you didn't have to use machine learning to do this, but they probably did. So I'm trying to explain how the machine is thinking, but it's not necessarily the case that it was doing exactly that. So let's talk about machine learning in general now. So the first step in machine learning and teaching a computer to do something, teaching it to learn, is to make a bunch of what's called training data. So like you're exercising the computer, this machine learning program. So you're going to mark the data that you want your machine learning model to learn. So maybe you're like, here's a face, the eyes are open. Here is a face, and I'm going to mark it that the eyes are closed. And you're going to give the computer a ton of pictures of faces. And you have pre-labeled them for eyes open and eyes closed. Yeah? That's your training data. Okay? And most often you label that data. There are some forms of machine learning where you don't label the data, so like you just give it these things and like tell the computer to figure out the difference, which is a very fun thing to think about, but most often the data is labeled. Okay? So again, if you want to notice faces, you'll give it a bunch of labeled pictures with faces and non-faces, or if you want to notice eyes, you'd give it a bunch of pictures of eyes open and eyes closed. Yeah? That is the idea. So like if you're trying to determine whether or not you see a face, you give it like a picture of a face and, I don't know, maybe a picture of an airplane. Whee! And have it differentiate between the two. Yeah? That's the idea. So that's step one. You have to have a ton of training data. That's quite nice and unfortunately hard to get sometimes. Step two is to train your model, right? You're getting ready to train it, and now you're training it. And you use some kind of machine learning technique. The hot one these days is using neural networks, but you don't have to use them. You can use just normal statistical methods. That is the hardest word for me to say for some reason. Where you do different things. I'd be happy to tell you about those in office hours. But a neural network is fun because it kind of models the brain. Like it has a bunch of little neurons, and they take input, and they like fire information between each other, and eventually they like decide on an output, which is fun. That is essentially a tiny little brain with a bunch of little neuron cells that have been modeled as software pieces. So that is the training process. You just kind of give this to your little virtual brain and have it like figure out the difference. Usually you have to train it a long time, okay, for a long time. Your model starts out being very, very poor, so it's like, okay, everybody has eyes open. That's essentially what's going to start thinking when it sees all these pictures, and it's going to be very wrong like half the time if half of your pictures have eyes closed. So the beauty of machine learning is you don't have to write the program to be like, okay, go in the middle of the face, look for white. That is not necessary for a neural network. It's just going to go and figure out the difference on its own. It can learn from its mistakes. That's the beauty of machine learning. You can have it learn from its mistakes by just continuing to run it and continuing to train it. Let's make sure I'm still recording, yes. Okay, so that's the second step. The third step is to test your model on a separate set of data, because it probably got really good at this data, your training data, because it's memorized it. And we want to make sure that it's not just memorizing things. We want to give it a brand new face that looks slightly different and make sure that it can tell when the eyes are open and the eyes are closed. That is the idea. So you test your model on a separate set of labeled data, and then I have no clue why this is cut off. Sorry about that. So let's see what I was trying to say here. I think I can just leave it at that for now. We want to make sure that it's getting those things right most of the time, right? So on these new faces, making sure that it didn't just like memorize this stuff over here, and it actually got these faces correct. It's like, okay, yes, the eyes are open. So that's essentially machine learning in a nutshell, and it's not too bad. The hardest part is actually step one. It is usually super, super difficult to get a lot of training data. And now you know why you are the product and why you get a bunch of things for free on the internet. Because Google Photos, for example, they're about to not be free, unfortunately. Sad day. But they let you put as much of your, as many images as you want on their website. And the reason they're giving you all that space for free is so that they can train their machine learning tools. Yeah? That is the only reason. They otherwise would not have an incentive to take all of your images and host them for you. Yeah? So they're not just being nice, they're getting training data for free from that. Yeah? It's in the terms and conditions. Okay, so that is a quick primer on how machine learning works. Now let's talk about like how people are using machine learning. So I guess machines in general, they're very, very good at doing the same thing over and over again without messing up. Yeah? They know exactly how far to move their little mechanical arm. Like, you can move it a little bit, you know exactly to move it by like 5 degrees or something, and now it's over here. And it's ready to like grab this other thing if this was like some kind of grabbing tool. Who knows? So machines are super good at this, so much better than humans, right? They have a tiny, tiny chance of failure. Maybe they run out of oil or something, or their parts break down over time. But on the whole, they are a lot faster than humans, and they're more precise, which is unfortunate. So machine learning is taking over manufacturing, and it has probably taken over most of it by now, right? That is the point. And it's a very unfortunate thing for us humans, unless we like really, really hit universal basic income hard or something, because people are getting replaced by this, okay? Let's remember that. It costs a lot of money to make one of these robots and to train it and make sure that it works, but the second you've made one, you can make another if it breaks, and you know exactly that it's going to work for quite a while, okay? So it's going to do its job much better than a human would. It costs a lot of money up front, but you never have to pay a salary to a robot, okay? So that is a social issue that we really need to fix recently, or soon, if we don't want to all be out of jobs, yeah? So that is factory robots. That's a very good example of machine learning today. Okay, now let's talk about games in the last few minutes before we get to your essay. This is really fun. So Jeopardy, the show, it is quite popular, and it's only for humans, right? They get asked questions on a display, and you also hear it from the announcer, right? And you have to answer a bunch of just random questions about different topics. So this is not a specialized thing. So it's hard for a computer to get good at this kind of stuff, but we have made one get good at it. So this is probably what you're thinking about if you've heard of Watson, who competed on Jeopardy, made by IBM. This is probably what you're thinking about when you think about an intelligent computer. It's like, okay, it can talk. It knows the answers to questions. That is textbook artificial intelligence in my mind, right? So it was made not too far in the past. In 2005, they started working on it. And what Watson does is it uses natural language processing, which is a new kind of machine learning. It's fun to think about. It uses that to decipher questions, to break down, like, okay, where is the subject in the sentence? Where's the verb? Oops. What's the question word going on? Etc. What's the object? Etc. That's what it's doing. It is looking at the text or listening to the voices and figuring out what the questions are and answering them based on a huge database of information. So this computer has a giant hard drive, and it knows a lot of things. It's just remembered a bunch of text. So, for example, when it went on Jeopardy, they didn't connect it to the internet because that would be cheating, but it had so much space in it, it like had the entire copy of Wikipedia, yeah? Among other things, right? So it's crazy how much information you can stick inside a computer these days, and it was using that to answer its questions. So Watson, in a sense, is breaking down the question and coming up with a bunch of different options for the answer. So like answer 1, answer 2, this is how it's thinking, answer 3, and it has a confidence level for all of these answers. Like, okay, answer 1, I have a 10% confidence level. Answer 3, I have a 5% confidence level. And maybe for answer 2, we have an 85% confidence level. And so if the confidence is high enough, it chooses it and guesses that answer, and it won a lot of money that way. Okay, so I encourage you to watch this video. It's just showing how good Watson was. So it goes to show that machine learning is getting good at general purpose intelligence, which is something that's very, very hard, okay, for a machine to do. Specialized intelligence is really easy for a computer these days. So before Watson, the cool thing about computers was that they can play chess really, really well, okay? And more recently, they can play Go really, really well. So back in the 90s, in 97, it was a very, very huge deal when a computer, for the first time, it beat a world champion. It beat Kasparov. Back in the day, here is Kasparov over there, and this was insane. This took the world by storm, because suddenly computers are able to think so hard they can beat grandmasters. Okay, they can beat humans. They are finally on the level of another human. And chess is a fun one. I can kind of explain how chess works inside of a computer, how it's thinking. I think that's maybe 4 or 5, 6. Whatever, let's pretend this is 8 squares. Who cares? So here's your chessboard, right? You have a bunch of options. You have the option to like move the piece there. You can move that piece there. You can move that piece over here. You can also move it like less than that. You can move this piece up here maybe, or right here. You have a ton of options in chess, and the idea of a computer is breaking down all those options. So it's like, okay, take this game board, and okay, the game could progress like this, and then it's the other user's turn, the other player's turn. And you have a bunch of different states that you can go to. Like, okay, from here you can move this piece in this way. You can move this piece in this way, and the game board looks like this. This is what the computer is doing. It is enumerating all of the possibilities to a certain depth, because you can't go forever. Otherwise, you'd run out of memory. But the computer was so good at thinking in the future, it just chose the best option. It's like, okay, if I choose this option, then I'm going to win the least amount of time, or I'm going to fail. I'm going to lose the least amount of times. I'm going to win the most amount of times. That's the idea. That's how it was thinking. So this is how the computer beat a chess grandmaster. And more recently, if you want to watch this video of another world champion getting beat, we had the game Go, which is not 8x8 anymore. It is huge. Like the game board for Go is much, much bigger. So, and the options are huge. So this is why it took a lot longer, took until 2017 to beat the world champion there, because the computer, again, had to enumerate all the possibilities. Like, okay, I could move over here, I could move over here, and figure out which one was the best. It needed more memory. And so we had to wait for Moore's Law to get us there. Yeah? That's the idea. So we got good at these kind of games, and these are very specialized games. Okay? That's why they're easier than general purpose knowledge for a computer to think about. Okay? So that's the idea. And the beauty of machine learning for games like this, like chess and like Go, the rules are so clear that a computer can play itself. Isn't that crazy? It's like, okay, I'll be white on this turn and I'll be black on this turn. That is the point. It can play itself and get better based on noticing what happens when it loses and noticing what happens when it wins. It can come up with the most crazy strategy that it has proven over time to work. It doesn't have to use any chess books. It just knows. It can learn from itself. That's the beauty of it. And with that, that brings us to our essay, which is a bit different. It's not about artificial intelligence. Maybe in the future you'll have one about that. But I want to give you an essay on fallacies. Okay? So let me go back to the slide. Let me pull up your essay, and then we'll talk about it, and we'll get out of here after that. Okay, welcome back. So here is your essay. It's the longest one yet. It's going to be an 1,000-word essay, but don't worry, because you're going to copy and paste a lot of stuff, so it's going to be less than this really for you. So what I want you to do for this essay is to find fallacies in arguments posted on social media. Okay? Pick any website you want. Twitter's probably the most easiest one, probably Facebook too. There are a ton of fallacies in the world. Okay? There is a larger list that you can totally look at and use these fallacies when you are writing this essay. Okay? So I just want you to write about a bunch of little fallacies that you find. Okay? So if you'd like, you don't have to, but if you'd like to talk about topics relevant to this class, you can look up people trying to talk about like robots taking people's jobs, self-driving cars, they're either good or they're going to kill us all, things like that. Here are a bunch of hot topics that have to do with technology, but you don't have to use those if you don't want to, if you find something easier. What I'd like you to do is write an essay, of course, with 1,000 words, but I want you to have a specific kind of structure this time, okay? So I want to make sure that you get enough fallacies, not just like talk about one the whole time, okay? So definitely an introduction and a conclusion paragraph. You don't have to do anything special with those, but just include them. But in the middle, the meat of your essay, what I want is for you to find at least 5 fallacies on the internet, and you'll write at least a paragraph about each of them. Okay, so at least 5 fallacies is what I want to see in your essay. Okay, so you're going to quote the post, so that'll take up some words, which is nice, and then I want you to analyze why and how that post contains a fallacy. Okay, one thing that's very, very important that I want to stress very, very hard, and I did back in when we were talking about the fallacy slides, every fallacy has a name. Okay, like this one is false dilemma. It has a very, very specific name. You can't just say, oh yeah, this is a fallacy because this person wasn't thinking properly. Every fallacy has a name. You've got to give the name. Okay, so definitely look into the lecture notes and the Wikipedia link. You don't get credit if you don't have the name of the fallacy. Okay, so just find the fallacy on the internet, quote it, analyze why it has that particular fallacy. That's all. Okay, so that's essentially all you have to do. There's one additional requirement because, unfortunately, the internet's a horrible place. Ad hominem, people making fun of each other or just like being mean to each other, is the easiest fallacy to find. So you should have at least half of your post being something other than ad hominem. Okay, that one's too easy for all of them. So just keep that in mind. These are all the directions that you have to follow. I want you to have fun with it, and I also want to give you an example before we go. So I tried to look up Phoebe Bridgers, thinking that people who respond to people on Twitter, people who respond to famous people, usually can sometimes write fallacious things. So that's where I started looking, but I ended on the president because that's a better place to look for fallacies, I found. So if we go to the president's Twitter page, we'll find that he retweeted the vice president most recently. Happy International Women's Day, by the way. He retweeted her saying that she wants to honor all the women who have been working for the past year in all of these fields to protect us. Like they're all these women who are risking their lives, right? So that is what the vice president said. And then we're going to make fun of Dave the misogynist because Dave responded this: just the women, guess that would be typical of you. I want to thank all who risk their lives for others. So this is an example of, and this is exactly what I want you to do in your essay, this is an example of the straw man fallacy. Because Dave is trying to make the case that the vice president doesn't care about anyone who is not a woman right now, okay? Which is absolutely not true. I'm pretty sure that the vice president cares very much about all Americans. But she just wanted to highlight the women because this is International Women's Day. Let's make it about them for once. So she saying that had nothing to do with the fact that she was discrediting anybody else who risked their lives and was not a woman. Okay, so that is essentially all you have to do for your essay. Find little examples like this and talk about what kind of fallacy they are and analyze why. That's all. Why do they match the definition of that fallacy? So that is your 1,000-word essay, and hopefully it's not too bad because you get to like copy and paste all these things and talk about like how this all got set up, right? So hopefully you'll find fun little examples of fallacies like this, and yeah, that's all I have for you. So good luck. Please yell at me if you have any questions, and I will see you in the programming lecture.